Welcome back. This is Sinha. Last time we left every oscillator alone after a single nudge, and each one died away in its own fashion. Today, nothing gets left alone. The outside keeps pushing over and over, and everything depends on the rhythm of that push. Match the rhythm, and tiny pushes build into something enormous. Today, we meet resonance, the most dramatic thing a spring can do. I asked you to bring something breakable. Here is mine, a thin wine glass. Tap it once and it rings, a teen note that fades in about a second. You already know that fading ring. It is last lecture's under damped fate, a cosine trapped inside a shrinking envelope. The glass is a spring with a beautiful voice, and like every spring we met, once nudged, it dies quietly. Now, instead of tapping, hold a steady note at the glass, exactly at its own pitch. Watch the rim. The tremble grows, pass after pass, each cycle adding a little more than friction takes away. The held note itself never gets louder. Only the timing is special. Hold that thought, because near the end of this lecture, we will finish what this note starts. You already know the secret from the playground. A swing is a pendulum, and tiny pushes, correctly timed, built every great flight you ever rode. Push at the swing's own rhythm, and each shove adds to the last. Push at the wrong rhythm, and your effort cancels itself. Rhythm beats strength. That, in one sentence, is resonance. And today, we earn the whole story with honest algebra. Here is the plan. First, we add the outside push to the master equation and hunt the motion that survives, the steady state. Second, we map the response against the driving rhythm and find the famous peak. Third, a strange 90-degree twist hiding at the top of that peak. And fourth, the quality factor. Q, the single number behind designs from car suspensions to a breaking glass. Before the new force takes the stage, line up the family we already own. The bare spring first, no fiction anywhere. Newton says x double dot equals minus omega 0 squared x, and the answer is a pure cosine that never dies. The machine keeps perfect time forever. Every valley in physics hums this note. Add the drag we met last lecture. The master equation grows its 2 gamma x dot term, and the cosine picks up a dying envelope. Every free oscillation now ends at rest by one of the three fates. Ring, glide, or ooze, the story always closes quietly. Now, the newcomer. Keep the spring, keep the drag, and let an outside force push in rhythm. F0 cosine omega t. Three forces share one block. The spring pulling home, the drag taxing speed, the push that never tires. What happens? That question is this whole lecture. Let Newton collect all three forces, then divide by the mass, the same tidying as last time. X double dot plus 2 gamma x dot plus omega 0 squared x equals little f cosine omega t. The slide defines little f as the push divided by the mass, just bookkeeping to keep the lines clean. Every other symbol is an old friend. Now look closely, because two different frequencies live inside one equation. Omega 0 belongs to the machine, built from its spring and its mass before the drive ever arrived. Omega belongs to the outside, chosen freely by whoever pushes. They know nothing about each other. The whole lecture is the story of their negotiation and of the spectacular thing that happens when they agree. One more gift before the hunt. The equation is still linear, so solutions still add. Last lecture's privilege carried forward intact. That has a consequence bigger than today. Any periodic push, however jagged, can be built from a stack of cosines. So solving one cosine drive quietly solves them all. We take the single cosine today, and we bank the rest for later arcs. Before any algebra, watch the machine. Switch the drive on with the block sitting at rest, and let the drive run slightly off the machine's own note. The start is a mess. Two rhythms fight inside one motion. The swing swells and shrinks, a lopsided wobble with no clean shape anywhere. If you expected instant elegance, this honest mess is what nature serves first. Now simply wait. The mess fades. Slowly, the block settles into a perfect steady swing that repeats exactly, cycle after cycle, as far as we care to watch. Run the experiment again from a completely different launch, a sharp shove instead of a rest start. The opening chapter looks completely different. The ending is identical. The machine forgets its launch every single time. Superposition explains it. The full motion is one particular solution that follows the drive, plus some free motion of the machine itself. And free motion is exactly what we classified last time. Every one of the three fates dies away exponentially. So the personal part of the story dies, and the drives part alone survives. The dying opener is called the transient. The survivor is the steady state. And notice the quiet coup. The steady state swings at omega, the drive's own frequency, not at omega 0. The outside always wins the rhythm war, always. The machine still gets a vote, but it votes differently by deciding how big the response is and how late it arrives. Those two numbers are the real prize, and we go hunting for them right now. We hunt with last lecture's best weapon, guess and verify. The drive is a cosine at omega, so the response should be a cosine at omega as well. That much the rhythm war already settled. But the playground warns that the response may trail the push. So guess x equals the amplitude A times cosine of omega t minus phi. Then let the equation itself tell us whether the guess can live. Two dials, both unknown. The amplitude A says how wide the steady swing is. The phase phi says how far the swing trails the push, measured as an angle around the cycle. Feed the guess through the master equation, one derivative at a time, every line on the slide. When the dust settles, every term lands in one of two piles, the cosine pile or the sine pile. The unlock is a single identity, the cosine of a difference, expanded honestly on the slide. With it, the whole left side sorts into two families, the terms that ride cosine omega t and the terms that ride sine omega t. Now look at the right side. The drive is pure cosine. It brings no sine term at all, and that lopsidedness is about to do all the work. The equation must hold at every instant, not at one lucky moment. The two shapes are independent, and no amount of one can imitate the other. So each family must balance entirely on its own. Two families give two equations, and we hold exactly two unknowns. The algebra has organized itself, and the next slide collects the prize. Take the sine family first. It balances only if the lag is tuned exactly right, and dividing one family by the other kills the amplitude entirely. The lag drops out as one clean ratio, 2 gamma omega over omega 0 squared minus omega squared. The slide writes it as a tangent. The delay is set by the machine and the rhythm, never by how hard you push. Strength buys size, not timing. For the size, square both family equations and add them. The two phi terms merge into one because sine squared plus cosine squared is 1. Picture it as a right triangle. The two families are the legs, the hypotenuse is the response r, and the amplitude A is little f over r. One triangle, and the entire lecture now lives inside it. Sanity before drama. push infinitely slowly, omega to 0. The formula hands back F0 over K, the static stretch, exactly Hooke's law with no lag at all. Push slowly, get statics. A new formula must first repay everything we already knew, and this one does it on demand, in one gray line beside the box. Now the drama. Set the damping to 0 and drive exactly at omega 0. The denominator vanishes and the formula divides by 0, predicting an infinite response. Real machines carry damping, so reality softens the verdict, but the warning stands. Somewhere near omega 0, something enormous is waiting. Let us go and look at it directly. Here is the whole story as one picture, the response amplitude drawn against the driving frequency. On the far left, slow pushes, and the curve starts at the static stretch. On the far right, frantic pushes, and the curve dies toward nothing. Between them rises the mountain, the famous peak, standing almost exactly at the machine's own frequency. Every driven system in physics owns a picture like this one. Now vary the damping and draw the family. Heavy damping gives a gentle hill, hardly worth a detour. Ease the damping and the peak sharpens and climbs. Light damping builds a tower. The height at omega 0 has an exact value, worth boxing. The response there is little f, over 2 gamma omega 0, and that number has a name waiting for it just ahead. Compare the peak to the static stretch, and the ratio collapses into a single number, omega 0 over 2, gamma. We call it the quality factor, Q. Drive a machine at its own frequency, and it answers Q times larger than a steady push of the same strength. For a door closer, Q sits near 1/2. For a kitchen glass, Q reaches 2000. One honest footnote. Resonance means driving at omega 0, where the lag is exactly 90 degrees. The amplitude peaks where the response R is smallest. Set the derivative of R to 0 and the summit lands a hair below omega 0, a shift of a fraction of 1%. Every engineer calls the peak omega 0 and sleeps well. Remember the mountain, remember its height, Q, and watch it work in the flesh. Watch resonance choose. One beam, shaken gently, at one steady rhythm, and 7 pendulums hanging from it, each a little longer than its neighbor. A longer pendulum keeps a slower clock, so along the row, the natural notes ramp from quick to lazy. One pendulum, just one, has exactly the length whose clock matches the shake. Every one of the 7 feels precisely the same driver. 6 of them barely tremble. The matched one grows, swing after swing, until it owns the beam. Nothing chose it but timing. Frequency match, not strength, decides who answers, and the mismatched neighbors are left almost still while their twin flies. This same selection is how a radio pulls one station from a crowded sky, a story for another course, but the identical physics. Now look at the end state, because the row has drawn something. Line up the settled swings and their heights trace a familiar shape. Small, small, rising, enormous, falling, small. Each pendulum sampled the response curve at its own natural frequency. So the row of clocks has drawn our mountain in the air. The resonance curve is not an abstraction. Hang enough pendulums and you can see it. Problem 1. The promised 90-degree twist. Draw the phase lag beneath the amplitude curve, sharing the same frequency axis, and read it end to end. For slow drives, the lag sits near 0, the block moving in step with the push, the spring quietly in charge. For very fast drives, the lag approaches 180 degrees, the block moving dead against the push, inertia now in charge. Path the drive exactly at omega 0 and read the lag there. 90 degrees exactly. And here is the astonishing part. It is 90 degrees for every damping, heavy or light, because tan phi blows up precisely where omega meets omega 0. Damping decides how quickly the phase curve sweeps through the crossing, but the crossing itself is pinned. Nature nailed the middle down. What does 90 degrees mean in the flesh? A quarter cycle ahead of the position is exactly in step with the velocity. At resonance, every push lands. While the block is moving away, never fighting position, always feeding speed. No effort wasted anywhere in the cycle. You have known this since childhood. You pushed the swing as it passed you, moving away every single time, and physics was keeping score. The twist also explains the tower. At 90 degrees, the spring force and the inertia cancel exactly, and the slide's balance sheet shows the cancellation line by line. The drive is left arguing with drag alone, and against small drag it wins enormously. The divide by zero we met earlier was this same cancellation, seen from the algebra side. Resonance is what remains when a machine stops resisting itself. Problem 2. Interrogate the two ends of the curve, because each end is ruled by a different piece of the machine, and knowing the ruler is the fastest way to design anything. Drive far below omega 0 first. The block simply rides the spring, stretching and relaxing in step with the push. The response settles at F0 over k, and the mass has vanished from the answer entirely. Why should the mass vanish? Because slow pushing is a statics problem. Nothing accelerates hard, so inertia never enters the negotiation, and the spring alone decides how far each push reaches. Stiffness rules below resonance. Down here, if you need a bigger response, softening the spring is the only dial that does anything. Check it on the curve. The low end never moves when gamma changes. Now drive far above omega 0. The push reverses so quickly the block barely moves at all, and the sliver of motion that survives runs dead against the push. The response falls as F0 over m omega squared, and now the spring has vanished instead. Fast shaking is an inertia problem. Mass rules above resonance, and doubling the drive rate buys a fourfold smaller answer. Put the three regimes side by side, and the curve becomes a map. Spring ruled on the left, mass ruled on the right, and in the narrow middle, where stiffness and inertia cancel each other, drag alone rules the peak. Notice that gamma appears in neither limit. The gray audit line makes the point. Damping matters only near the summit, which is exactly where Q lives. And Q is next. The quality factor has earned a closer look. The definition is one line, Q equals omega 0 over 2. Gamma, the machine's own frequency measured against its rate of dying. But a definition is cold, and this number is anything but. Q has three faces. You can see and even hear, and a machine shows you all three, whether it means 2 or not. Face 1. Q counts the rings. Cut the drive and let the lightly damped machine die freely. After Q full swings, the amplitude has fallen to about 4%, practically silence. A kitchen glass rings near 600 Hz for about 3 seconds. That is nearly 1800 rings on the way to silence, so Q sits near 2000 and you just measured it with nothing but your ears and a clock. Phase 2. Q multiplies the push. At resonance, the steady swing is Q times the static stretch straight from the boxed peak height. And the build-up is honest work, not magic. Starting from rest, the resonant machine needs about a third of Q cycles to reach 2/3 of its final swing. High Q machines answer enormously, but they insist on taking their time to get there. Phase 3. Q narrows the aim. The width of the peak, measured at half power, is omega 0 over Q. High gain and narrow aim are the same number wearing two costumes. A machine that amplifies 1,000-fold answers only 1/1000th of the frequency axis. So precision is the entry fee for power. And Q keeps one more face in the language of energy waiting for us in Lecture 10. Problem 3. Your car is last lecture's door closer rolled onto the road, a spring and a damper under each corner carrying about 300 kilograms apiece. Comfort Engineering tunes each corner near 1.2 Hz, a gentle walking rhythm. And a real road is not one bump. Expansion joints arrive every 12 meters, pushing the wheel like a metronome whose tempo is set by your speed. Divide speed by spacing and the road turns into a driving frequency. At 52 kilometers per hour, the joints arrive at 1.2 Hz, exactly the suspension's own note, and the car wallows and floats. There is a resonant speed, and every driver on a washboard road has discovered it, one worst speed, where the ride is at its roughest. Slower calms it. Faster, strangely, calms it too. Damping is the design dial. With a feather damper, the resonant bounce reaches 5 times the road's own ripple, seasick in 100 meters. Tuned to a quarter of critical, and the peak drops to exactly double, settling cleanly after each bump. Push far past critical, and a new problem appears. Every sharp pebble transmits straight to the cabin. The full road to cabin bookkeeping adds a wrinkle we set aside today, out loud. Audit the extremes. Far above the resonant speed, the response falls as 1 over omega squared, so highway speed over short ripple rides smoother than crawling over it, a thing every gravel road driver has learned by accident. And the deeper lesson stands. A comfortable car cannot remove resonance, only choose how politely it happens. Heavy enough damping does flatten the peak away, but a cabin that's stiff would feel every pebble. Problem 4. And the hook's debt comes due. The glass is an oscillator, so treat it like one. Ping it, and it rings near 600 Hz, taking about 3 seconds to fade to near silence. That dying ring is phase 1 of Q at work. 1800 cycles to die means Q near 2000. No instrument touched the glass. The measurement was made entirely by listening. Now drive it. A singer holds the exact pitch and phase 2 takes over. The rim's steady swing builds toward 2000 times the static push of that sound. A pressure that would flex the rim by a fraction of a hair now swings it thousands of times farther, past the strain the material can survive. Halve the Q and the same feat needs double the drive, the gray check on the slide. Phase 3 is the catch, and it is why the trick is hard. The singer must hold the pitch within about 1/3 of 1 Hz, the bandwidth of Q2000 at 600 Hz. On the full response curve, the target is the hairline. Look through the lens, and the hairline opens into a true peak with real shoulders. The width exists. Only the zoom can show it to you. So watch the whole story at full size. The note holds, patient and exact. The rim swells, pass after pass, a resonant ring up in slow motion, phase 2 compounding before your eyes. The swing crosses the strain the glass can bear, and the glass lets go. Resonance was never louder sound. It is patient timing, compounded 2000-fold, and the fragments are the receipt. 1831, a bridge near Manchester. Soldiers cross marching in step, the deck answers in step, and the swing grows until bolts shear and the bridge falls. The Army's standing order ever since says break step when crossing a bridge. It is an anti-resonance regulation written into military law decades before the physics had a proper name. Timing, once again, beats strength. 2000, the Millennium Footbridge, opening day. Thousands of walkers and a gentle sideways sway near 1 Hz. Here is the twist worth remembering. People steady themselves by stepping in time with the sway, so the crowd locks onto the bridge's phase, Perfectly timed pushes. Problem 1 at civil scale. The growth feeds itself. The bridge closed within 2 days and came back 2 years later full of dampers. One honest boundary before we celebrate too much. The most famous film of all, the Tacoma Narrows collapse of 1940, is usually shown at this exact moment. But the wind that day was no metronome. That failure was a self-feeding twist, a feedback story, genuinely different physics. Resonance is the right first chapter for understanding it, and it is not the whole book. The ledger for catastrophe turns out to be short. Growth per push is linear while the phase stays locked. Damping caps the growth at Q times the push. So disaster needs only three ingredients: patience, a locked phase, and a Q that is too generous. Break the step or break the phase, and the whole cascade dies on the spot. That is engineering's oldest cheap victory. 3 habits to carry out of today. First, transients die, so hunt the steady state. Every launch is forgotten, and the survivor moves at the drive's rhythm, never the machine's. When a problem hands you a periodic push, skip the messy opening chapter and solve directly for the ending. The beginning was never going to last, and the mathematics knows it. Second, resonance is a phase story. The peak is tall because at omega 0, the push rides the velocity, spring and inertia cancel, and only drag stands between the drive and the sky. So when you meet a dangerous resonance, ask the sharp question, what is left to resist it? The answer is only the damping. And that answer designs everything from door closers to skyscrapers. Third, one number, Q. It counts the rings, it multiplies the push, and it narrows the aim. 3 faces of omega 0 over 2 gamma. Gain and fragility always travel together, no exceptions on offer. When you meet a sharp and dramatic response anywhere in physics, reach for Q first. It will usually be holding the whole story, all by itself. Next time, the coupled dance. Today, the outside pushed us around. Next lecture, oscillators push each other. 2 pendulums share one support. They trade their swing back and forth in slow, hypnotic beats, and hidden inside that trade are special motions that never trade at all, the normal modes. They are the natural language of every vibration you will ever meet. That wraps up this lecture. This is Amit Sinha. Thanks for watching the Sinha Foundation channel. See you in the next one.